So, yeah, welcome to this last presentation for today, talking about the state-of-the-art research with Queens. Of course, everything I'm going to show is not my own research. Some of it I'm involved in, others I'm not even involved in. You will see the names and you will see references to the individual contributions of these research topics. Um, and some of the main contributors into to research with Queens so far, let's say, have been Maximilian Dinkel, Lea Heusel, Jonas Nitzler, and Gilles Robert-Lauret, the current maintainer team of the software. I will come back to that also later again. So if we talk about doing research with Queens, then one of the concepts just to motivate why do we want to do that? We have today seen a couple of tutorials on using the core concepts and core principles of doing multi-query analysis. But if you want to do that with more complex models or in higher dimensional spaces and everything, problems become much more challenging. And so, of course, one of the biggest challenges is extreme computational costs associated both with the forward model evaluation, but more importantly, also in this multi-query setup. You might have limited or noisy data. You have want to consider the model error as an epistemic uncertainty. And last but not least, you want to scale to the full cluster and really make use of an HPC cluster. And so this is just a small collection of images showing that. I've mentioned also previously that if you run your simulation thousands of times, you should expect them to fail, even in cases where you don't predict it in advance. There's always some odd things going on, and so you need to be aware of that. That's one of the biggest challenges. On the one hand, we have talked a lot about the infrastructure in Queens and how it can help tackling these problems, but to a certain degree, that's only very limited, and we only touch the surface on one of the aspects, and that's the methodological approaches, right? And so this aspect is something we haven't fully covered in the tutorials, and I just want to give a brief overview and brief flavor of what we do. So Queens was initially developed kind of to do research in this area and to tackle also some of these problems, for example, the computational cost with the methodological advances. And so there's approaches to do dimensionality reduction, to tackle the high dimensional input spaces, to do adaptive sampling such that you get the best out of the few samples you can do, right? You want to choose the ones that give you the most information, for example. A key technology is surrogate modeling that we haven't touched upon as well. And last but not least, a very strong research area for Queens is multi-fidelity methods, where you combine models of different fidelity um, to reduce the computational cost. Um, so all of this summarized, kind of, we have looked into this infrastructure for multi-query analysis. It takes a lot of time to set this up, and we hope to motivate that you don't have to do that again, and you can build upon this infrastructure. And I want to show you now also the methodological advances that you get kind of for free afterwards, because the research results are published in Queens as well. So if we publish a new method, then typically we also publish it as a new iterator in Queens, and so you can use these advanced methods in Queens straight after publication. We have seen this slide before, just through these two different scenarios of uncertainty and how to quantify uncertainties, and that we have these different approaches of doing forward uncertainty quantification, where we are interested in propagating the input uncertainty through the model to get the uncertainties in our output. That's one example, and the other example is the backward uncertainty quantification, where we have some prior knowledge of our inputs, but we get measurements of our output, and then we want to find kind of an update and the best fitting distribution for our inputs that describe the measured output together with the model. And so we are interested in identifying the input uncertainties. And both of these are kind of we do research and develop new methods in there. Just two examples for the forward uncertainty quantification to give you an idea on what we do. And this is all usually in combination with 4C, to be honest. So in this example, for example, Jonas Bieler has done a study where he changed the thickness of an aneurysm according to a random field. So the thickness of this aorta here is randomly distributed, and then you can kind of compute the stress and strain distribution based on these variations of the thickness. And you can see that it kind of substantially influences the results, and you want to kind of quantify the uncertainty because you won't be able to measure the thickness out of the out of the medical imaging data, so you kind of always have some uncertainty in there. Another approach, and that's really like a huge methodological advancement, is done here by Jonas Nitzler et al., where they do a multi-fidelity uncertainty quantification for complex physical models. In the paper, they show, for example, a fluid structure interaction problem. Where they learn kind of the relation between these models of different fidelity in a probabilistic sense, and it shows that there's usually a good agreement and a simplified agreement between these models that you can learn quite efficiently, and thus save a lot of computational cost in doing uncertainty propagation with complex, very expensive models. For Bayesian inverse analysis, we have also a couple of research progress. And on the left, you've shown, I haven't mentioned that in the previous slide. Let's just go back. So just some collection of available methods kind of that you find in Queens that are readily available, including, of course, the research results shown here. So the same for Bayesian inverse analysis. And again, then as a follow-up to this uncertainty quantification, so the forward problem, Jonas afterwards did improve and continue his work and to do this multi-fidelity approach to solve the inverse problem, which is typically even more challenging, especially if you have expensive forward models that don't have gradients. And you want to do this in high stochastic dimensions. Just as a side note, I think right now he also published this paper, or it's submitted at least. So this will be out soon in the full the final work. High stochastic dimensions here usually means a random field. So we want to identify a random field from measurements, which is a very challenging problem. Where does this, for example, also occur? Again, an example from Maximilian Dinkel here in this case, where they solve this Bayesian inverse problem with constrained Gaussian processes as a surrogate model, and including again an active learning approach just to get down the number. It's always the goal to get down the number of forward model evaluations of the most costly forward model. And here they show an example of identifying a random field on lung simulations. Another example from biomechanics, where Sylvia and Barbara did a study on tumor growth, and they tried to identify the parameters of a multiporous media model for tumor growth from actual measurement data. So that was really interesting, and that's done with Queens. And then some outlook kind of again, we're combining results from different physical simulations, and there you can really see again this multi-physics nature of 4C coming in, right? How can you combine knowledge from different fields to get an improved convergence of your Bayesian inverse analysis? Not only do you want to maybe sometimes quantify the uncertainties, but you also want to work with these uncertainties. And I just brought like two small example scenarios where we exploit these uncertainties, for example, in a global sensitivity analysis, which kind of builds upon this uncertainty propagation problem, where we have uncertain inputs, we propagate this uncertainty through our model, we get outputs, but we don't know which of these inputs have influenced the most the model, the uncertainties in the model output, and that's precisely what global sensitivity analysis does. It kind of identifies the influential and the uninfluential parameters of this model output. So influential parameters would be parameters that cause a lot of uncertainty in the model output, right? And uninfluential parameters are parameters that vary but don't influence the output a lot. On the other hand, another example where we exploit uncertainties is optimization under uncertainty, where the goal is to find a set of parameters that could influence, for example, the distribution of our inputs or the model directly. And these parameters, we want to identify these parameters that optimize a specific objective function in this uncertainty framework. Okay, some example studies. Again, here a very nice paper where I was also involved, a study that Barbara did, is global sensitivity analysis for biomechanical models. Again, we build a lot on surrogate modeling techniques. A key aspect here is that we can identify also the uncertainty in the predictions of the global sensitivity indices. And this is exemplified with the tumor growth model. Another study done by myself is global sensitivity analysis for aneurysm growth. So the quantity of interest here is the maximum diameter of this aneurysm that you saw growing in this little video over here. And then we can identify the parameters that are influential. Just to give you a hint on how this looks like. So we've studied here, I think it was 10 or 11 parameters. And what we find is that only actually 3 parameters influence this growth of the diameter substantially. Well, what is it? 7 of these parameters are uninfluential, right? So they literally have almost no influence regarding the uncertainty in the output. And so this can help you a lot. If you identify these parameters in this way, can help you a lot in reducing the complexity of your uncertainty propagation problem. Regarding optimization under uncertainty, there's an ongoing work by Max Dinkel and Gilles Robert-Ourey on the dynamic learning rate decay for stochastic variational inference. Stochastic variational inference is it's a type of algorithm to solve uncertainty propagation problems, where you have to learn, where you have a learning rate which influences the convergence a lot, and so you want to kind of balance it out and be most efficient in identifying the best learning rate. Yeah, so they are working on improving in this regard. And another a study by Gilles on identifying an optimal microscopic infrastructure for solid state batteries based on different particle size distributions, and finding kind of the best distribution to get the best properties of your solid state battery. I've touched upon this a couple of times. One of the key technologies to solve probabilistic problems is surrogate modeling. The idea behind a surrogate model is that you find an approximation of your true model. So your forward finite element model, for example, you find a approximation that yields a similar prediction, but in much less computational time or with much less computational effort. And so what we then do is we replace our original model with the surrogate model to do the uncertainty propagation problem. Why do we do that? Because in uncertainty propagation problems, we have to evaluate our model tens of thousands of times sometimes. And if we have an expensive model, this is prohibitively expensive. While if we get a surrogate model that gives us the same prediction ideally, but with less computational time, then this gets viable again. So this is the key idea, and it's always a core part of doing all of these approaches is finding proper surrogate models. And so Queens offers a lot of these techniques and a lot of different surrogate modeling techniques. It's a whole research field on its own. And you will see a couple of papers that I already shown here again, actually, because all of them under the hood work with quite advanced surrogate modeling techniques and surrogate models. that are all available in Queens for you to use and to train your own model on this. So just a selection here of papers again that have worked with surrogate models and that we've already seen before. Yeah, and last but not least, maybe a short outlook, kind of, because that's a core concept as well that we have implicitly touched upon. Because if you are doing inverse analysis, you're typically working with three experts, because you will have experimental data, so you will have someone who's doing experiments, getting you some data. You will have a modeling expert who has developed this advanced, really nice model, but it's not, we don't maybe know the parameters yet. So we want to combine that and we want to identify the model parameters, for example, from the experimental data. And the best approach to do this, in our experience, or well, let's not say the best, but one of the approaches that is very, very capable and promising is this probabilistic Bayesian inverse analysis. And so you also need an expert on doing that. And we'd like to think that Queens is a good framework to getting all of these experts together, working in a framework and combining that. And to do so, collaboration is, of course, extremely important. So probabilistic methods help bridging this gap between experimental studies and modeling by exactly bringing these two together. So the kind of last message I want to give, Queens can help you automate your research. You can use it for all sorts of things. It doesn't have to be these super advanced things. You can also use it to probe your freshly coded up models, do some parameter sweeps, do verification and validation. Can automate parameter studies for your publications or model comparison between different models on the same and the same circumstance and the same conditions. So whenever your model is evaluated many times, you can use Queens to do so with all the backbone infrastructure that we have looked into a lot. What you get for free then is you get like all these advanced analysis methods, so you can essentially build upon that and do follow-up studies if you want to. So just some ideas on doing that. Yeah, with this, I'd like to kind of come to an end and say thanks again to all the community and all the contributors. And again, this is just a small group of people who are just very active right now, but there's also a lot of contributors that are not shown here, which you can find on the GitHub list and on our community side. So thanks also for again for Regina and Bisha specifically, who have helped a lot today in setting up the tutorial, for my maintainer colleagues that are have helped setting up the slides and everything. If you want to keep in touch, you can always do so on GitHub. And so I wanna also point back to 4C and Queens. So because one of the key things that we wanted to show during this workshop is that actually these two tools work very well together, and we have done a lot of successful research with that, and we hope you can too. Feel free to log into GitHub, give us a like, start the project, open a discussion, say hi. If you have any questions, yeah, just let us know. We are happy to help, to engage and discuss. And yeah, with this, I'd like to thank you for your attention and for all the other organizers who have done and set up this workshop together with me. So thanks, Georg, Matthias, Regina, Gilles, Ingo, and Christoph, and Bisha. And thank you for participating, staying here up until the end. And I hope you enjoyed this. So thanks, everyone.
So thanks, Sebastian, for